Today, I want to talk about QR codes and explore how they work by writing my own QR code generator in Python. They have become such an everyday item in our lives, but how much do we really know about them? For example, before looking into QR codes, I've always thought that they work similar to barcodes. The lines on the barcode just denote this number right here, and when you scan it, you can look up what item is stored under this number. So I thought that the pattern on a QR code is essentially also just some number or identification, and when it's read, the camera or the reader looks it up in a global registry. So this one would store a YouTube link, for example. Maybe like a big Python dictionary where the pattern or the number is the key and the value is whatever you want it to store. But I wouldn't be making this video if it were that simple. Instead, they come with an intricate format pattern that helps the camera identify and read it. Also, there is no need for a registry because they encode and store the data on their own, so you can use them completely offline. And they have a way to protect themselves against damage or misread pixels. Then they also use a mask to ensure maximum readability. As you can see, there is a lot to unpack here, and initially I only wanted to make one video on this topic where I show how I wrote my QR code generator and maybe make some nice animations to complement it. But in order to be able to properly cover everything, this had to become a much larger project. So we're gonna split this journey up into 3 parts. Today, we'll talk about the general structure of QR codes, create the necessary format, and encode our data to pixels. In part 2, we'll go over error correction and masking. And in part 3, we'll generate larger QR codes and account for stuff like codeword interleaving. We'll start down here at the beginning, and by the end of this video, we'll have cleared the first stop of this climb. Going forward, we'll use these 3 QR codes as examples. The left one simply carries a hello world. The middle one is the YouTube link from before. And the right one is a virtual business card. If you scan this QR code with your phone, you can, for example, store this person as a contact. You can pause the video and scan them for yourselves. We'll talk about how they actually store this data in a bit, but for now I want to focus on the format. Let's start with the obvious one. The codes are all different sizes. The left one is 21 by 21 pixels, the middle one 33 by 33, and the right one 49 by 49. This is because they are all different versions of QR codes. In total, there are 40 versions, and we can calculate the side length for each version using this formula, where V is the version of the QR code. Or we can rearrange this formula to get the version from the size. If we plug in our side lengths, we can see that the left code is version 1, the middle one version 4, and the right one version 8. Before we move on, I want to implement this in our code. I wrote this QR matrix class here that for now only takes in a version and calculates its size using our formula. Now that we know the size, we can also have it store the matrix as a 2D array. I'll go ahead and replace the zeros with a pixel object. For now, it will only have a value that is either 0 or 1 and is 0 by default. I know it seems a bit useless now, but we'll expand on that later. And we'll also need a method to export the code to an image, so I went ahead and wrote that too. This first creates a canvas that is the size of our matrix, and then it goes through the matrix, checks the value, and places either a white pixel for a 0 or a black pixel for a 1. In the end, we'll just resize the image to a more reasonable size, like 2000 by 2000 pixels. And if we run this code, we can indeed see an empty white matrix. So far, so good then. Going back to our example QR codes, let's talk about these ears. These are called finder patterns and are located in the three corners of the code. These tell the camera that it is looking at a QR code and help reading it correctly when, for example, the code is on its side. Back in Python, we can add a method for these finder patterns. Starting in the top left corner, it first draws the horizontal lines, then the vertical lines, and then the black square in the middle. We'll place them in this new method called add format. One starts at 0, 0, and for the other two, we have to set one of the coordinates to size -7, since we start drawing the pattern from the top left corner and the side length is 7 pixels. And running the code, we can now see that the QR code is starting to take shape. We can also change the version, and we see that the patterns indeed get smaller as the code gets bigger. Next, I want to tackle these alignment patterns. They are similar to the finder pattern, and for larger QR codes, these further help the camera to orient the code. By measuring the distance from the alignment pattern to the corners, we can figure out at what angle we are looking at the code. So even if it's skewed like this, or like this, the lines have a different length to the starting position. This way, we always know how we would need to unskew the code. We can also see that our three QR codes all have a different number of alignment patterns. How many a QR code has depends on its version. Version 1, like the left code, doesn't have one at all. The version 4 code in the middle has a single one, and this version 8 code has 6 of them. Basically, the bigger the code gets, the more alignment patterns we need. That makes sense because for a smaller QR code, even if we haven't unskewed it perfectly, a lot of the data will still be fine. But larger the QR code gets, the finer the pixels are, and we need to be more precise with this flattening. Let's show this with an example. Say we scanned these two codes at some weird angle and we did our best to unskew them, but as you can see it's not quite perfect. So our reader thinks the QR codes it is reading look like this. Now let's see what kind of data we would get. For this, we'll just take the average color of each square where we think a pixel should be. Then we get something like this. Now, QR codes don't really work with gray values, so we'll make every pixel that has a brightness of 50% or less black, and we'll turn the other pixels up to white. So again, this is the code our camera has read. But we can already see that it's not quite correct. The finder pattern in the top left corner, for example, is wrong. If we compare the data to the data that is actually stored in the original QR codes, we can color all the pixels that have been read wrong. It would look something like this. And if we count up the error, we can see that about 12% of pixels have been read wrong for the left code, and about 21% for the right code. So we see why we need to be more precise with our alignments as the code gets bigger. Because even in this perfect example, we start losing more and more data the bigger the code gets. Now, enough explaining. Let's write the alignment patterns. Similar to the finder patterns, I wrote this add alignment pattern method. Again, we will draw the patterns with these for loops. But the key difference here is that this method takes in the center point instead of the top left corner. This will make some other logic down the line easier to implement. Back in the add format method, we can place the alignment patterns at the correct place. Again, the coordinates are size -7 to place them in the bottom right corner. However, as we know, version 1 doesn't have an alignment pattern, so in this case we just skip this step. Now, some of you may be wondering, what do we do if we're supposed to add multiple patterns? Well, that question we'll have to answer in another video. A lot of the placement logic and encoding gets quite a bit more complicated when we move to bigger codes, as we already saw with the alignment patterns before. So for this video, I want to focus on versions 1 and 2. The other 38 versions will unfortunately have to wait for part 3. But much of the logic, like the encoding or placement that we're gonna implement today, are valid for all versions. So for now, it will be much easier if we only talk about versions 1 and 2. Looking at the full code here, we can run it and see that for version 1 nothing really changed. But that was to be expected. If we up the version to 2, the alignment pattern starts to appear. Now we can input higher versions and the pattern does scale with the code size, but we'll still just get 1 since we haven't implemented that logic yet. Back at our example codes, if we look closely, we will notice that all of them have these 2 strips of alternating black and white pixels. These are called the timing strips. Because this is an easy pattern to follow, the reader can count these pixels, and since the number is dependent on the size of the code, we can figure out what version of QR code we are looking at. So we know how much data to expect. And I'll also throw in the last pattern, since it's really easy. It's this pixel right here. This is called the dark module. Basically, it's just leftover pixel. Because of the way QR codes are structured, there is always 1 pixel too much in the matrix that we simply don't have any data to fill with. So by convention, we just set it to black. These are both simple patterns, so I went ahead and added them to our code. For the timing strip, we just go along the lines and set every other pixel to black. The method for the dark module is a bit overkill, I admit, but I wanted to stay consistent with our current layout. We'll add these 2 methods to our add format method here. And this is how our code looks now with all of the format. Let's have a quick recap. Our code currently can create the matrix and add the finder patterns, the alignment patterns, the timing strips, and the dark module. Now, we're not done with the format just yet. There is actually some extra format in purple here, but that actually depends on what we want to encode. So we'll have to come back to this later. For now, let's move on to the interesting part, how to encode our data. Before we go on to the encoding process, I just quickly want to mention this website right here, thonky.com. It has a full tutorial on how to create QR codes, and it really helped me when making the initial code for this project. So if you're following along, definitely check it out. All of the tables I will be using in this video come from this website as well. Depending on the data that our QR code should store, we can choose between 4 encoding modes. Numeric for numbers 0 through 9, alphanumeric for capital letters, numbers, and some selected special characters, byte for all 256 characters of the Latin 1 set. This is the mode used to store links since it supports lowercase characters and pretty much all of the special characters. And kanji, obviously for Japanese kanji because the QR code was originally invented in Japan. Since our QR code's area is obviously limited, we also have to think about capacities. The more characters a mode allows to be encoded, the less capacity it offers. Obviously, we can choose a more efficient encoding algorithm if we only have to deal with numbers than if we have to encode 256 symbols. In this video, we'll mainly focus on the alphanumeric mode, since it's a good trade-off between space efficiency and complexity. But we'll also briefly touch on numeric and byte mode. The kanji mode we'll disregard completely right now. Maybe I'll include it in another video. Again, for simplicity, we'll use the phrase hello world that we want to encode using alphanumeric mode. For now, we don't know how to do that, but luckily we have this mystery machine here that will do it for us. The encoding process can be a bit difficult to follow, so I want to show you the full picture before we try to code it. The machine turned our phrase into a bunch of ones and zeros. These are the so-called code words and are the pixels that will be placed in our matrix. I'll rearrange the screen a bit so we can analyze this string a bit more. To not get overwhelmed, let's lose these last bytes. These are the error correction code words that I want to ignore for now. So we're left with a much more manageable data string. Looking into the QR code specifications, it says that the first 4 bits are for the mode indicator. Basically, each of the 4 encoding modes has a unique 4-bit identifier. We place this at the very beginning, so the reader knows how to decode the data. Since we're using alphanumeric mode, we get 0010. The next 9 bits are reserved for the character count. This is just the number of characters we want to encode as a binary number. In our case, the length is 11, or 1011 in base 2. The remaining zeros to the left are just to ensure the length of 9 bits. Now, the next big chunk of bits is actually the encoded phrase. We'll have to write this alnum function ourselves later. And the rest is just some formatting again that we'll get into later. But to break it down, our data string can't be too short. The matrix expects the data string to be a fixed length, so every space in the matrix gets filled. If our message is too short, we just pad to the needed length with some given code words. We'll use this as a cheat sheet to check our work when we try to implement this in our code. I'll start by creating an encoding mode class. So, what actually makes up an encoding mode? Well, first, it needs a mode indicator. Then, it needs the length of the character count. In my short explanation before, I didn't really go into it, but how long the character count itself is also dependent on the mode and the version. For this, we can just look at this table right here. So for versions 1 through 9, the character count is 9 bits for alphanumeric mode. For versions 10 through 26, it's 11 characters. And from 27 all the way up to version 40, it needs to be 13 bits long. And similarly for the other encoding modes. Let's implement a method to be able to look up these numbers. We just take a version, and depending into which of the 3 intervals it falls in, we return the corresponding length. Then, lastly, it needs an encoding function. And using this method, we can encode our data. So we can go ahead and create the 3 encoding modes we will be covering today. All we need to do is input the parameters we just talked about. Next, I'll make a data string class. This will take in a phrase and compute the finished code words. For now, we also need to know the version of the QR code and the encoding mode. Similar to the QR matrix, we'll wrap all the functionality into this createDataString method that will manipulate the data string. Now, with the setup done, we can start with the mode indicator. This method will just look up the identifier of the chosen encoding mode and place it at the beginning of our data string. Next, we add the character count. We just append the length of our data as a binary number to a data string. But we need to make sure it has the right amount of bits. So we'll look that up and pad our data string if necessary by passing it as a second argument into this binary function. I just wrapped the built-in format function into this more readable version that we'll use for converting into binary. Now onto the interesting part. We'll go ahead and write the encoding function. I already wrote the functions for numeric and byte mode, so if you're interested in how they work, you can pause the video and have a quick look. Here, for the alphanumeric function, I only added this check that throws an exception if we try to encode data with invalid characters. Let's talk about how the alphanumeric encoding mode actually works. I'll replace the white space, that is also a character that we need to encode, with the box, just to see it a bit better. So first, we split up the phrase into these pairs. Then we look up the index of each character in our lookup, and multiply the first index by 45, and add the second one. In our case, that gives us 779. This number then gets converted into an 11-bit string. This is the basic process that we now just have to repeat for all the remaining characters. If we have an odd number of characters, like in our case, we just add the index of the last character as a 6-bit binary number. If we take the binary string we get from this process and compare it with what we have written down for the encoded data, we can see it matches perfectly. Implementing this in Python is also pretty simple. The lookup I made from a dictionary where we can use our characters as the key to get the index. Then we just loop through every pair and look up the indices. Those we add together with our formula and append the converted number to our data string. Again, for the case of an odd number of characters, we just append the binary index of the single character. I'll also write the method to add this encoded data to our datastring class here. If we print our current datastring, we see that it matches with our cheat sheet. We could also change the parameters and print the datastring for byte mode. We can already see that the mode indicator in the beginning changed, and the character count is still 1011, but in this case it's 8 bits long instead of 9. And the rest is again just the encoded data. All we need to add now is the formatting I mentioned earlier. And for this, we need to talk about error correction. Remember the code words I discarded earlier? Those are error correction bits, and they are located right here in the code. These give QR codes their seemingly magical qualities, like that they are still readable even if a part of the information is missing. So even if the QR code is damaged, or a part of it is covered up by a logo, these bits help reconstruct the data. You can think of them as redundant information. So in a way, these bits also hold whatever we put into our data code words, and if we for whatever reason can't correctly decode one of these code words, we can just refer to the error correction. Now, how much lost data we can recover with the help of these error correction bits depends on the error correction level. Low can reconstruct 7%, medium 15%, quartile 25%, and high up to 30%. But a high error correction level also comes at a cost. We need more of these code words. As you can see, for high we have more error correction code words than data code words, so we trade capacity for readability. The version of QR code dictates how much physical space we have in the matrix, and the error correction level, how much of this we can use for data storage. And for the format we're about to add, we need to look up this data capacity. This can be found in this table right here. Just take the number of data code words and multiply it by 8, since a code word consists of 8 bits. Alright, before we go any further, let's actually implement this capacitor number in our code. I'll go ahead and create an error correction level class. Similar to the encoding modes, the error correction levels also have an identifier. Only it's 2 bits now instead of 4. What I will also add is a method that can look up the data capacity of this error correction level when given a version. I have all of the tables we're using in this video in an Excel file, and I made this lookup function that returns the value of a given cell. With this, we can now create the 4 error correction levels with their respective identifiers. So with this implemented, we can talk about how the format is made. Here we have our current data string without the format. If we compare its length to the required length, we see we're still a bit short. For this demonstration, I chose version 1 and the quartile error correction level. This is what determines the required length, that is 104 bits in our case. First, we need to add a maximum of 4 terminator zeros. These tell the QR code that the data has entered here, and the rest is just format and error correction bits. I say a maximum of 4 because if at any point we would reach the required length, we just stop. For our data string here, we need to add all 4, and that brings our length up to 78. Next, since we're working in code words, which are 8-bit strings, we need to make the length of our data string a multiple of 8 too, so it can easily be broken up into code words. Let's rearrange the string back into code words to better see that process. As you can see, we're still 2 bits short of completing this last code word here. So again, we just fill it up with zeros. Here, we don't need to check if we're exceeding the required length, since it's also a multiple of 8, so the values will coincide anyways. But we're still 3 code words short of the required length. So lastly, we will add some repeating code words. These are just the numbers 236 and 17 as binary strings. And we continue alternating between the two until we reach our needed length. In our case, we just need 3 though. With this, we have all our data code words. Back in Python, I updated our data string class to now also ask for an error correction level. I also wrote this add format method. It first looks up the required amount of bits using the method we wrote earlier. Then it adds a maximum of 4 zeros to our data string and checking if we've reached the required length after each step. Here we keep on adding zeros until our data string has a length that is a multiple of 8. And then we keep on adding these alternating padding bytes until we eventually hit the end. Now, all that would be left to do is generate the error correction code words. However, that is a bit complicated, and I don't want to end the video with pure maths. So for now, we'll just say they came from our mystery machine and carry on. But as a side note, the code words are generated using Reed-Solomon encoding, and there are even libraries for Python that do exactly that. So for anyone following along, you can just use this setup right here to generate these code words. Again, we'll dive into how they actually work and how to generate them in the next video. Now, how the placement works is that we will derive a pattern that covers all the empty pixels in the matrix. And then, starting with the first bit, we will place them in our matrix following this pattern. There are 3 simple rules for placing the pixels in the matrix. The first one says to follow the zigzag pattern right here, and if we hit either edge of the matrix, we just start a new column and turn around. Now you will notice that with this rule alone, we get this leftover edge here on the left. We can't really fill it with our pattern because it would be going off the matrix. But we're going to fix that with another rule in a minute. So this would be the placement in an empty matrix. But our matrix is not empty. We already placed some format bits, so we need to account for that. The second rule tells us to just skip over pixels that are part of the format. We don't place anything and move on to the next free pixel. I've marked those pixels green so we can still see our pattern. And now to fixing this singular column on the left. Notice how going over the vertical timing strip, we have this weird alternating pattern of placing and not placing. This is because the strip partially overlaps with our pattern. Here, we'll just move 1 pixel to the left and kill two birds with one stone. Now we don't have this jumping around the timing strip, and we fill out the column on the left. So in total, our pattern looks like this. These rules stay the same for all versions of QR codes, so adding an alignment pattern, for example, won't mess up anything. Let's implement this data placement in our code. First, I want to have a way to mark a pixel as part of the format. Now it will come in handy that we made this pixel class in the beginning. I'll give it another attribute called format, and if that is true, we won't place any data there. I'll also write these two methods to make the code a bit more readable when using this. I've already updated all our add format methods to not only set the values, but to also mark the pixels as part of the format. For the finder pattern, we also marked surrounding pixels as part of the format. These are the separators that I didn't mention in the beginning when it wasn't really relevant, but you can think of them as part of the finder pattern. And we also need to mark the format strip. This is the part of the format I am putting off because we still lack one crucial element of QR codes to be able to implement that. However, we still need to mark it so our data placement works. For this, I'll just go over the area and set the pixels to be part of the format. In the future, we'll expand on this method and add its proper functionality as well. And here is the method for placing the data. We first apply rule 1 and set our starting position to be the bottom right corner. Then we calculate the next step in our zigzag pattern and apply it to our position. After this, we do rule 3 and check if we're at the vertical timing strip. If we are, we move over by 1. And finally, here we have rule 2. If the current position isn't occupied by a format pixel, we place the next element from our data string. And this is how it looks in action. Obviously, we don't see the white pixels being placed on the white background, but if we compare it with our animation here, it's safe to say we get the same matrix. The only difference is the format information, which we haven't implemented in our code yet. We could also change the parameters again, and then we would get this QR code. I think this is a good point to end the video here. I'll pan through the entire code on the left here, while we take a look at our current QR code. All in all, our work is really starting to take shape. But we're still missing the format information in purple here, and I still owe you the explanation for the error correction code words. Also, some of you might have already noticed that our QR codes, even though they are mostly done, don't really match the finished scannable ones. This we'll have to fix by applying masks in the next video. So with this first stop in our journey completed, and many things added to our to-do list for part 2 and 3, I want to thank you very much for watching. See you in part 2.